Today we are going to talk about Black-Scholes option pricing theory. So the main tool we're going to use is continuous time finance that we learned earlier in this course. So what is Black-Scholes formula? So we start with the value of the underlying stock option, and we also have a bond, and we calculate the value of an option, and we will start the call with a call option. The standard approach to get the valuation of the call option is the dynamic replicating portfolio strategy. But in this class, we were not going to follow that approach. Instead, consistent with the previous methods earlier in this course, we will follow the discount factor approach. In other words, we will use the discount factor each date, and then price the stock and a bond and use the discount factor to price the options. So how do we do that? So we begin with the call option payoff. So C is the price of the call at time t. And this call option has the expiration date of capital T. So the payoff on the expiration date is given as following. So it is the maximum between these two quantities. And you can express it in terms of so-called hockey stick. So on the x-axis, you have the stock price on the expiration date, and on the y-axis, you have payoff of the call. And when the strike is X, the payoff of the call option is given as like this. So this is basically max okay. Now we will assume that the underlying stock follows the geometric Brownian motion. In other words, as we have seen before, so the stock price at time t is simply stock price at time 0 e to the mu okay, and we assume that the Brownian motion starts from 0. Okay, so that is our assumption. And we also assume that there's a money market account with an instantaneous interest rate R dt. So in other words, this R is the instantaneous risk-free rate. Okay, and because expectation of the stochastic discount factor at time t should have the drift rate of negative R dt. Okay, so the risk-free rate is going to restrict the drift rate of the stochastic discount factor. Okay. Now, given this setup, we will define the discount factor or the stochastic discount factor. And as before, we will use lambda t as the stochastic discount factor. Okay. And it has the following functional form in this fashion. Okay. So in the discrete time case, we use the stochastic discount factor m. And remember, we can use the projection. So x star is the projection of m on the payoff space, okay? Then the key thing is that this x has all the pricing information as in m. In other words, for any payoff x that is in X, the price of the payoff is basically is given like this, but that's the definition of the stochastic discount factor. But X star has the same set of information as M. Why? Because this is okay, and this one will be zero because W is the orthogonal component to the payoff space, right? So basically, when you have a stochastic discount factor, by projecting onto the payoff space, you can get the same pricing information as the original stochastic discount factor. So in the continuous time analog, the following holds. First of all, how is the stochastic discount factor in continuous time defined? First, the drift should be negative of R. I mean, there's a typo. It should be negative of R, like here. The drift is negative of R. And the second thing is this thing here. That is the market price of risk, which is basically the Sharpe ratio. Okay? The volatility term in front of the Brownian motion should be the same as the market price of risk. And then another thing to note is that the sign is negative. In other words, when Z is positive, let's suppose the market price of risk, this is positive, okay? Now let's suppose that is the case. Suppose DZ is positive, okay? Suppose DZ is positive, meaning, okay, what is Z? Z is the shock to the stock price. Okay? So when DZ is positive, stock return is going to be high. Okay? When DZ is positive, the S over S is also positive, right? So positive shock in Z is also a positive shock to the price, stock price. But that's a negative shock to the stochastic discount factor, correct? So when the stochastic discount factor is low, okay, it means the good state of the world. Okay, it means the good state of the world. When the marginal utility is low. Okay, so this asset S has a negative correlation with the stochastic discount factor. Okay. In other words, this asset S pays off. In other words, the stock S pays off, is going to have higher returns when in good times. Okay, this is a stock that pays off well in good times, and it pays off poorly in bad times. In other words, the expected return on the stock should be positive, greater than the risk-free rate. Okay? So that's why the market price of risk is likely to be positive. That was the underlying economics of this stochastic discount factor. Okay? Another thing to note is that another thing to note is that we assume that this is a orthogonal component to the stock price, right? So basically, this is like W here. This is like W here. So we can pretend that this doesn't exist. Okay. So the shock to the stochastic discount factor that is unrelated to the payoff space, we can just ignore. Okay. And we can pretend that this dz is the only source of uncertainty in the stochastic discount factor. Okay. And there are two ways to solve it. Both will give the identical answers, but we will look at the following. The first one. The second one, we will only derive the partial differential equation, and we will know the known result that the solution to the partial differential equation is the same as the solution to the first one. Okay, so how do we do the pricing of the option? Okay, so remember, if in from the fundamental pricing equation, right? The price of any asset at time t is basically okay. So that was the property of the stochastic discount factor. Okay. So when there's no dividend, okay. Therefore, this should hold at time 0. Oops. Okay, and by dividing lambda 0, we obtain the equation here. Okay, so basically, call option price at time 0 is expected value of the payoff, but discount it back using the stochastic discount factor like this. Okay. And as we said, we will assume that sigma w is equal to 0, and the answer is going to be the same. Okay. And now we will solve the expectation directly. Okay, so we will solve this one directly. Okay, this equation here. Mm-hmm. To solve the expectation here, we need to calculate the value of this thing, the copy. Let me just put it here. Okay, so what do we want to do? We want to calculate the price of the call, which is basically okay, which is basically the expectation. So we need to calculate the expectation. Mm-hmm. What are the random variables here? So this is the random variable. This is a RV random variable. And this ST is another random variable, right? So we need to know the distribution of in ST. Okay, so that's all we need to know. We want the distribution of these two random variables. Okay? Let's first calculate the distribution of ST. Okay. So ST follows the following stochastic differential equation, and we know that solving this stochastic differential equation is can be done by considering the derivative of the log of the stock price using the Ito formula, right? And then that gave us, I think it's in lecture 3 on continuous time. And you must have seen okay. Therefore, log of ST equals log of S0 by, you can just integrate both sides from 0 to cap T. And this is what you get. Epsilon, where epsilon is basically, this is a normalized Brownian motion, okay, which as means 0 and 1. Okay. Therefore, the stock price at capital T becomes a random variable in the following fashion. Okay. Where epsilon is non-random variable. Okay. Similarly, stochastic discount factor is going to become okay, and epsilon is defined in a similar way. Okay, so these are the representations of these stock price and the stochastic discount factor. Okay? This looks a little bit complicated, but you will see later that is not much so. In other words, both ST and get lambda t over lambda 0 is log normal. Okay, both they are log normal variables, random variables. In other words, if you look at ST, right, ST is simply S0 over E, some constant plus sigma and the stochastic discount factor is also okay, some constant minus. Okay, so these are all log normal variables, so the calculations are possible. Okay, so what we did in the previous slide is basically we got that, okay, and using this, so basically what I have here is the calculation that I showed in the previous slide. So in general, a log normal um, the distribution or the geometric Brownian motion has a solution in the following form. Therefore, we have the closed form solutions for the stock price ST and the stochastic discount factor lambda t. Then we can calculate the integrals. Okay, so what is the integral? Now we know both the distribution, right? So we know this is a log non-random variable, okay? And we had previously max between s cap minus x comma 0. But if we change the integral from st equals x to infinity, we only have the case, we are left with the case only when this item is positive. Therefore, we can treat as if the integral is with respect to st minus x. Okay? So basically, let me show you the, okay, how the calculation will be done. So it is integral, so it should be from negative infinity to positive infinity of the stochastic discount factor and max of st minus x comma 0 over some distribution. Okay? But we will only consider the case. Why? Because otherwise the integral is going to be 0. So we can only consider when st is greater than x and okay. Now we know the distribution of this, right? The distribution of the stochastic discount factor is e to the negative r, what was it? A half and a half okay. There's no a half. Let me just copy it. Okay. Okay. Okay, so the stochastic discount factor is a square here and negative. Okay, that's right. And the stock price is given as S0 E mu minus sigma z squared over 2 P plus, okay. Then this integral here becomes, so this integral here becomes st from x to infinity. Okay, and this is e to the negative r epsilon. Okay, so that is this here, And then we're moving on to st minus x. That is going to be S0 e to the epsilon, and this is minus x. And then the last item, df, what is it? That is basically the density function for the normal random variable times the epsilon. Okay. Now so the question is how to solve this integral here, and the details calculation is basically done in Cochrane chapter I think it's 15 point. Okay, so that is in Cochrane chapter 15.2, I think. Okay, the chapter for the Black-Scholes formula. So that integral is one integral that you have to do at least once in your lifetime. Okay? So try it. So that is one way of calculating the Black-Scholes option pricing formula. The other is solving backwards. Okay, so this one is a little bit more complicated than the previous one. So we are not going to do the numerical solution here, but I will just tell you about the partial differential equation. Okay. So the idea is the following. The idea is that the option pricing is basically the function of two things, current stock price and time. Now we can use the Ito's formula to get the instantaneous change, and it's going to give us the following, right? This is the standard, the simple application of the Ito's formula. Okay. Now we will use the fact that from the fundamental pricing equation, okay, so the infinitesimal change in lambda times c is going to have a drift of 0. Okay? And we will also use the fact that the stochastic discount factor has the drift of negative r. Okay. Now, what are we going to do? We are basically doing the following. Okay. So we know that this should be 0. Okay. So we will use that by using Ito's formula here. So it's d lambda times c plus lambda times dc plus d lambda dc. Okay, so that this is Ito. And we know d lambda. We know d lambda. Okay. How? D lambda over lambda has negative of the drift, negative of the risk-free rate as the drift, and we had the market price of risk as the diffusion term. And we know C from the Ito's formula, right? So dc was negative dc dt plus, I'm sorry, this should be plus, and dc ds plus a half. Now comes the Ito term. Okay, so this is dc. Okay. Okay. Now we know that dc and d lambda we can calculate from here. Okay, so we plug d lambda and dc into the expression here. This is what we get. And that is what's called the That is what's called the Black-Scholes differential equation. Okay? In other words, you calculate this thing here, and we know that expected value of d lambda dc should be 0. This means that the drift, the dt term of d lambda times c should be 0. Okay? And using that condition, we get the Black-Scholes differential equation like this. And you can solve this equation numerically, okay, but we are not going to do that. But the good thing about the Black-Scholes case is that there's an analytical solution, especially when the boundary condition satisfies this. That is what's called the Feynman and Keck formula. That's going to give you the same formula that we did in the method 1. Okay, so for the detail of the Black-Scholes formula calculation, see Cochrane related chapter.